So in this video, what I'm going to show you how to do is I'm going to show you how to use RSA encryption to, one, create a public and private key, two, to encode a short message. In this case, we're only going to encode a single number, and three, then show how to decode using the public and private key. Okay? So what we're going to need to do for encryption is first, we're going to have to choose two prime numbers. Okay? Choose two prime numbers. And for our purposes, I'm going to use some small ones. All right? In general, in RSA encryption, you use really large prime numbers because then it makes everything harder to crack. So we're going to choose two small ones for demonstration purposes. We'll choose P equals 17, and we're going to choose Q equals 53. Okay? Then what we'll do is we're going to create a value N. And N is going to equal P times Q. So that's going to end up equaling 901. Right? 17 times 53 is 901. The next thing that we're going to need to generate is we're going to need to generate phi. And what phi is phi is going to end up being P minus 1 times Q minus 1. In our case, that's going to be 16 times 52, and that's 832. All right? So we pick two primes. N will end up being the multiplication of those two primes, and then phi will end up equaling P minus 1 times Q minus 1. So go ahead, you can try that out, generate a pair for yourself. Now that we've done that, what we need to do is we want to find E, which is relatively prime to phi. Meaning that the GCD of phi and E is going to equal 1. So the GCD of phi and E is going to end up equaling 1. Now, one of the things that I want to do is when I'm creating E, I don't want to pick a really small number for E because that actually makes my calculations really unwieldy if I'm doing kind of like doing this stuff by hand. And not only that, it might make it really easy to decrypt. So what I'm going to do is I'm actually going to go through and I'm going to create a factor tree for 832. Okay? And that's going to be 2 times 416, 208 times 2, 104 times 2, 52 times 2, 26 times 2, 13 times 2, and now we've actually got a prime factorization for 832. And that ends up being 2 to the 6th times 13. So that's 832. To be relatively prime with phi, which is 832, I just need to pick a number that doesn't share any factors with 832. So what I'm going to do is I'm going to select 3 cubed. Okay, so I'll let 3 cubed, which equals 27. Okay, I can see that since 3 cubed and 832, which is 2 to the 6th times 13, don't share any factors, the two of them are going to end up being relatively prime. So E in this case is going to equal 27. All right, so that's how we're going to pick E. Generally, what I'll do in order to pick E is I will go out, I'll create a prime factorization for phi, okay, and then select a number that does not share any of the common factors with 832, or with phi in this case. Next up, what we're going to do is we're going to find the multiplicative inverse of E mod phi. So we got E mod phi, all right, and we're going to call this D. So how we're going to do that is we're actually going to utilize the Euclidean algorithm. We're going to generate a linear combination and then find the multiplicative inverse. Okay, so we're going to do this by hand because it's one of those skills that kind of handy for doing number theory. So E was 27, and we're going to find 27 mod 832, right? Because that's what our phi is in this case. So 832 is going to equal 30 times 27 plus 22. Then we'll get 27 equals 22 times 1 plus 5. Then 22 will equal 5 times 4 plus 2. 5 will equal 2 times 2 plus 1. And then finally 2 equals 2 times 1 plus 0. And so that ends our Euclidean algorithm. Okay? Now we'll use this to find the linear combination. We'll start out here at 5 equals 2 times 2 plus 1. So that'll be 5 minus 2 times 2 equals 1. Then we'll move up to the next equation, and we'll get 22 minus 5 times 4 equals 2. I'm going to now get a substitute in for 2 here, so that's going to give me 5 minus 2, and we'll get 22 minus 5 times 4 equals 1. Simplifying, I get 5 minus 22 times 2 plus 5 times 8 equals 1. And so that gives me then 5 times 9 minus 22 times 2 equals 1. All right, so that's now fully simplified. So now I'm going to move 1 up. I'll get 27 minus 22 times 1 equals 5. And so now I've got a substitution. I'll substitute in for 5. So that's going to give me 27 minus 22 times 1 times 9 minus 22 times 2 equals 1. That's 27 times 9 minus 22 times 1 times 9, excuse me, minus 22 times 2 equals 1. So that means that 27 times 9 minus 22 times 11 is going to equal 1. Then finally we got the last equation here. That's 832 minus 30 times 27 is going to equal 22. Come up to that last equation. I plug that in. I got 27 times, equals 22, not 2, but 22. 27 times 9 minus, this will be 832 minus 30 times 27 times 11 equals 1. So that gives me now then 27 times 9 minus 832 times 11 plus 27 times 30 equals 1. So that gives me now then 27 times 39 minus 832. This is not 27 times 30, it's 27 times 330. So that gives me 27 times 339, right? Adding 330 and 9, minus 832 times 11 is going to equal 1. And now we're actually completed. We've got our linear combination of 27 and 832. Since we're looking for the inverse of 27 mod 832, that inverse here is 339. So the multiplicative inverse, D, equals 339. Okay, so we're going to utilize that method for finding the multiplicative inverse where we use the Euclidean algorithm, okay, and then form our linear combination from that Euclidean algorithm in order to find the multiplicative inverse. Now I have the entirety of my encryption. My public key is going to end up being N and E. And my private key, the one that I will give to the person on the other side, is going to end up equaling D. Okay? So in my case, N equals 901, E equals 27, and D is going to equal 339. And there we go. And so that ends up being my encryption key. What we need to do now is we need to actually go in and we need to actually encrypt using our encryption key. Okay? So we're going to start out, and I'm going to actually select, I'm going to use a number. I'm going to encrypt 801. The number 801. Okay? And we'll have a very special way of going about doing that encryption. So what I'm going to use is I'm going to create a number. I'm going to create C, right? That's going to be my encrypted value. That'll be my encrypted value. And it's going to end up equaling ME to the mod N. Okay? So I'm going to create a number C, and in my case, it's going to be 801 to the 27th power mod 901. So my goal here is to actually go through and do that encryption, to figure out what C is, okay, and do the encryption. How I'm going to do that is I'm actually going to utilize fast exponentiation, okay? So I'm going to start out with figuring out what 27 is in binary. So 27 is going to end up equaling, right, I've got 116, 18, no 4s, right, okay, 16, 8 is 24, 1, 2, and 1, 1. So it's 1, 1, 0, 1, 1. And that's what 27 is, okay? So what I'll do now then is I'll rewrite 801, and this is just to kind of get us thinking, 801 to the 27th is going to end up equaling 801 to the 2 to the 2 to the 4th times 801 2 cubed, 801 times 801, and we're not going to need 2 squared, okay? But we'll just have times 2 to the 1, right? Because that's the 2 to the 1, times 801, and this is 2 to the 0, which is just 2 to the 0, and it'll be mod 901. And so for the sake of, this is going to be 801 to the 27th, mod 901 as well. So what I need to do is I need to figure out what these values actually are, and it's not that hard to do, okay? Once we do this, all we want to understand is that each one of these terms is just the previous one squared. So what we're going to do is we're going to just continuously square and keep only the terms that we need, okay? So like, for example, we'll start out with 801, and then 2 to the 0 is just 801. So it's going to be 801 mod 901, and that's just equal to 801. Okay? Because 2 to the 0 is just a 1, same thing. Now we take 801, right? 2 to the 1, that's 801 squared mod 901. And when we go through and take 801 squared, that's going to end up equaling 89. Now, we now have 801, and we don't have any 2 squareds, but I'm actually going to find it because it's going to make my life a lot easier. Mod 901, that's actually going to end up equaling 801 squared. Mod 901. We already know what 801 squared is. It's 89. So that's going to end up being 89 squared mod 901. Okay, because that's what that was. And that ends up equaling, and that equals 713. Then I'm going to take 801 2 cubed mod 901, and that ends up just equaling 713 mod 901 squared mod 901, which ends up equaling 205. And then we'll take 801 2 to the 4th, that's the last term that we need, mod 901, and that's just 205 squared, so that's going to be 205 mod 901 squared mod 901, and that'll end up equaling then 579. Okay? So that actually gives me all of the terms that I'm going to need. Notice I'm going to need a 2 to the 4th, a 2 cubed, a 2 to the 1, and a 2 to the 0. Well, if you look here, the one that I'm not going to need is I'm not going to need the 2 to the 2 squared. So we'll eliminate that one. And what we'll do now is we'll just use some modular arithmetic in order to do this. So 801 to the 27th mod 901 is then going to equal 801. So this one, 801 mod 901 times 89 mod 901 times 205 mod 901 times 579 mod 901. All of this mod 901, which ends up equaling then 59. And that ends up being our C1. So C, or RC, so C equals 59. That is our encrypted value. And that's what gets sent over to the person who I am sending my code to. So what I'll do is I'll send, right? Okay, I'll send N equals 901, E equals 27, and then in some kind of private way or under a secure connection, I'll send over that D equals 339. Okay, and then here's the code C equals 59. Okay, and this is the encoded value. So what you can see here, we'll utilize that fast exponentiation. We find our binary term, right? 27 is 11011, right? And then we're just going to calculate these powers of 2, starting out with just 801, then squaring until we finish out all of our binary terms. Okay? Until we finish out all those binary terms. Once we've done that and we've calculated each one of those values, we just multiply them all together. Now, I'm going to give you another example. When we do decoding, sometimes this can be a little bit hard depending on the calculator that you're working with, that sort of thing. But what we'll do is we'll just kind of like break it up into more manageable pieces. Okay? But this is really all you've got to do. Okay? And then what we send over N, E, D, and C. Now that we've done that and we've encrypted to C, now we want to decrypt back to M. And so that's where D is going to come into play. Okay? So M is going to end up equaling C to the D mod N. Okay? And that's why D is so important. D is that private decryption key because that's going to allow us to do our decryption. So in our case, we're going to find M. M is going to end up equaling 59 to the 339th power mod 901. Okay? A little bit more complicated than the last one because that 339th power can make things a little bit rugged. But it's actually the same process. It's just going to take us just slightly longer. Okay? The first thing I'm going to do is I'm actually going to figure out what 339 is in binary. So 339 in binary is going to end up equaling 101010011. Ha! There we go. I don't have 339 memorized in binary. I went out and I figured it out beforehand. It's one of those things where, you know, part of knowing how to do this kind of decryption is figuring out a number in binary. So what that means is that I'm going to have 59 to the 2 to the 0th power, mod 901. Figure out what that is. I'll have 59 2 to the 1 power, mod 901. 59 2 squared, mod 901. And now, I'm not going to need all of these, which is fine, okay? But I'm going to find each one of them because actually it makes it really easy to do this kind of multiplication, right? Because it's just a matter of squaring continuously. I got 59 2 to the 4th, mod 901. 59 2 to the 5th, mod 901. 59 2 to the 6th, mod 901. 59 2 to the 7th, mod 901. And then 59 to the 2 to the 8th, mod 901. And that completes everything that I need. All right. At the end, I'm not going to end up needing the 2nd, the 3rd, the 5th, or the 7th, but just having them there makes this so much easier to actually calculate, right? So this is going to be 59. 59 to the 1, mod 901 is just going to be 59. 59 squared, mod 901, ends up equaling 778. Then we'll take 59 to the 4th, that's just 778 squared, mod 901, and that ends up equaling 713. Then we'll take 713 squared, mod 901, and that'll end up equaling 205. Then we'll take 205 squared, mod 901, all right, to give us 59 to the 16th, and that's going to end up equaling 579. 59 to the 2 to the 5th, mod 901, is going to end up equaling And by the way, if you're like, okay, I don't trust how this is working, you need to go find your modulus, go ahead and do that. Just pause the video, confirm that my numbers here are correct. Okay? They are. It's good news. This is 69 squared mod 901. And that ends up equaling, 579 squared mod 901. And that ends up equaling 69. Then we'll take 69 squared mod 901. That'll end up equaling 256. 256 squared mod 901 is going to equal 664. And 664 squared mod 901 is going to end up equaling 307. So there we are. Now we look at our binary representation. I'm only going to need this one, the second, okay, the third and the fourth. Those are zeros in my binary representation. Then I will need the fourth. There's a 0 for the fifth. The sixth will be included. A 0 for the seventh. And finally the eighth will be included. Right? And I get that from the binary representation of 339. 339, right, only has the 0th power, 2 to the 1st power, 2 to the 4th power, 2 to the 6th power, and 2 to the 8th power. Everything else is a 0, right? Makes life a lot easier when we need to go out and multiply. Right? Let me check that I have enough ones. 1, 2, 3, 4, 5. And it looks like I've got 5 circles. That's great. Okay? So 59 to the 339 mod 901 is then going to equal the multiplication of just the ones that I needed. All the other ones are zeros. So I'm going to get 59 mod 901 times 778 mod 901 times 579 mod 901 times 256 mod 901 times 307 mod 901. Ta-da! There we go. 1, 2, 3, 4, 5. Let's just check to make sure that those are the right 5. Yep, those are the right 5. Now, if you go in and you put in 59 times 778 times 579, oh, by the way, this is all mod 901, and you plug all of those in, you're going to get a very large number into your calculator, okay? And you may not be able to find what its modulus is. But what we can do is we can kind of do this step by step. We can start out, say, for example, by multiplying 59 times 778, okay? And then taking its modulus, 901. So we take 778 times 59. This ends up giving me, these two multiplied together, they end up giving me 852 mod 901, okay? Which is great. Then I can just multiply that by 579 mod 901 to give me the multiplication of the three of them. So now what I have is I have 461. These two multiplied together are going to end up giving me 461 mod 901. And what I've done now is I multiplied together the first three of them, okay? And I just need to now multiply 256 mod 901 times 307 mod 901, and then take that mod 901. And if I go through and I actually multiply those ones together, okay, what I end up getting is I end up getting this equal to 801. 801 mod 901, but just 801, which is what I started with. We've now successfully decrypted, okay? So you can kind of see the fast exponentiation here, okay? And then we just use some modular arithmetic where you can basically multiply terms together 2 at a time or even 3 at a time in order to kind of like allow your calculator to work if you're using like a handheld like I am right now and you kind of want to work through some of your modular arithmetic. Okay? So what we can see here is our decryption is going to be m equals c to the d mod n. Okay? And when we go in and we do that actual work, we end up back at where we started at our original value. Okay? So, when you are doing your RSA encryption, right, we are going to choose 2 primes. We'll choose 2 primes, call them P and Q, right? That's 1. 2, we're going to find N, which will equal P times Q. All right? Then 3, we'll find phi, which is going to equal P minus 1 times Q minus 1. Then we'll find an E such that the GCD of E and phi is equal to 1. Right? A relatively prime value E, right? And the GCD of E and phi ends up equaling 1. 5, right? Find the multiplicative inverse D for E mod phi. So then we're going to go find our multiplicative inverse D, okay? That gives me 6. My public key is going to be N and E, and my private key will be D. Okay, so there we go. Public key and an E, private key will end up equaling D. 7, our encryption will encrypt. That'll be C equals M to the E mod N. We'll use fast exponentiation in order to actually figure out what that is, right? And then our decrypt is going to be M equals C to the D mod N. And that is RSA encryption.